Building bridges in the U.S. blends cutting-edge engineering with bold ambition, connecting communities and shaping landscapes in truly awe-inspiring ways. The westbound span of the new Tappan Zee Bridge is nearing full connection across the Hudson River. Crews are working to join the main span at the center, creating an unbroken structure from shore to shore. Once completed, traffic will shift onto this new section, which features 8 lanes to handle vehicle flow. This span is wider than the future eastbound span, as it will also accommodate a shared path for pedestrians and cyclists. After the westbound span opens to traffic, the old Tappan Zee Bridge will be taken down, marking a major step in the transformation of this vital river crossing. Construction of the new bridge to replace the Tappan Zee relies on modular design for rapid assembly. Across the East Coast, large segments are fabricated and shipped to the site. Key materials, including precast panels, bearings, and electrical systems, are staged at facilities like Tompkins Cove and the Port of Comenius. At Comenius, steel beams are assembled into 400-ton units with pre-installed utilities, then transported down the Hudson River over 12 hours. These modules are lifted into place by iLift-NY, a massive floating supercrane. The bridge deck is built using over 6,000 interlocking concrete panels, each coated with polymer for durability. Construction progresses from both shores toward the center of the river. Main span towers are erected using jump forms, mobile platforms, allowing concrete pours and material assembly in vertical stages. Tower cranes support the high-altitude work. Enormous 700-ton connective beams are installed with precision between the towers. Workers face challenging weather and height conditions but follow a strict safety culture, with authority to stop unsafe actions. Stay cables, crucial for support, are also being installed. Meanwhile, noise barriers, pedestrian and bike paths, and cashless tolling improve the user experience. New maintenance and emergency facilities are also under construction to serve the future bridge efficiently. From autumn 2013 to summer 2014, construction crews of the new NY Bridge project made significant progress on the foundations of the twin-span replacement for the Tappan Zee Bridge. Throughout this period, massive floating cranes and hundreds of workers from Tappan Zee constructors worked continuously on the Hudson River. By the end of the first year, nearly 2/3 of the bridge's foundation piles had been installed. The work spanned all seasons, with foundation drilling and pile driving taking place during harsh winter conditions and continuing steadily through spring and summer, laying the groundwork for the new crossing superstructure. To install permanent cables, workers first ensure key components are in place. The anchor block under the deck, a formwork tube through the deck, and the HDPE protective pipe between the deck and the tower. The saddle is also precast into the pylon. Cable strands arrive on spools and are fed through the HDPE pipe using a pusher.
We give them a mat sheathing off.
A worker in a small basket guides each strand into the correct hole in the saddle using a detailed map.
They range from around 30.
Once positioned, the sheath is stripped, and the strand is anchored, ready for stressing. The Tappan Zee Bridge replacement began with the selection of a cable-stayed design, featuring a 1,200-foot main span to preserve scenic views. Construction started with foundation piers built in the Hudson River. Crews drove piles and poured massive pile caps, followed by reinforced concrete pier columns and caps. The floating crane, brought from over 6,000 miles away, played a key role throughout construction. Due to shoreline congestion, large steel components were prefabricated off-site and transported by barge. Towering 419 feet, the chamfered main span towers supported prefabricated deck segments and over 74 million pounds of steel and concrete. A total of 192 stay cables containing 4,900 miles of wire connected the towers to the deck. Once the westbound span opened, traffic shifted, allowing the old bridge's safe demolition. Final girder placement and precast deck panels completed the eastbound span. The bridge was tied to land with new ramps and a shared-use path, transforming regional transportation and offering breathtaking views. Construction of the new twin-span bridge began with massive steel piles being driven deep into the riverbed to form solid foundations. Floating cranes and barges transported construction materials and positioned them with precision. Pile caps and large precast concrete pier segments were then installed atop these piles, forming the base for the future towers and roadways. Crews built temporary platforms and trestles to provide access for equipment and workers during construction over water. The bridge's signature cable-stayed towers began rising from the piers, constructed incrementally using climbing formwork systems. Simultaneously, structural steel sections for the bridge deck were fabricated off-site and transported to the site using barges. The enormous left coast lifter crane played a crucial role by hoisting fully assembled steel girders, each weighing hundreds of tons, into position. These girders were installed span by span, reducing on-site assembly and minimizing risks. Once the girders were in place, crews began installing the road deck panels, followed by reinforcing bars, concrete pours, and barrier walls. Stay cables were carefully threaded and tensioned between the pylons and deck sections to support the bridge structure. Cable anchoring and tensioning were carried out sequentially as more sections of the bridge deck were completed. Lighting, drainage, electrical systems, and expansion joints were integrated into the superstructure during this stage. Once the first north span was completed, traffic was temporarily rerouted onto it, so the second south span could be completed in parallel. After both spans were finished and safety inspections were passed, all lanes were opened. Meanwhile, demolition crews dismantled the old bridge using cranes and barges. In unstable sections, controlled explosives were used to safely bring down remnants of the old structure, completing the complex multi-year bridge construction effort. In August 2017, the new Tappan Zee Bridge's westbound span officially opened to traffic. It carries westbound vehicles previously using the old bridge and temporarily accommodates eastbound traffic as well. This twin-span cable-stayed bridge is part of a major infrastructure upgrade. The eastbound span remains under construction, as its final connections cannot be completed until sections of the old bridge are demolished to make space. Full eastbound operations on the new span are scheduled to begin in 2018, once the demolition clears the way. The completed westbound span represents a key milestone in the replacement of the aging original bridge. The Governor Mario M. Cuomo Bridge, also known as the new Tappan Zee Bridge, is a striking twin cable-stayed bridge spanning the Hudson River between Tarrytown and Nyack, New York. Replacing the old cantilever-style Tappan Zee Bridge, it stretches 3.1 miles 5 kilometers and features two separate decks, each carrying 4 lanes of traffic. Its main span reaches 1,200 feet 370 meters, supported by elegant towers and radiating cables. Opened between 2017 and 2018, the $3.9 billion bridge also includes a shared-use path for cyclists and pedestrians. With a clearance of 139 feet 42 meters, it accommodates river traffic below. Its combined width of 183 feet 56 meters makes it one of the widest cable-stayed bridges in the world. Tolls are collected eastbound only, with variable rates depending on EZ Pass origin. The Margaret Hunt Hill Bridge is an iconic cable-stayed bridge in Dallas, Texas, designed by renowned architect Santiago Calatrava. Spanning the Trinity River, it connects the Woodall-Rogers Freeway to Singleton Boulevard in West Dallas. Its most striking feature is a 400-foot-tall steel arch with 58 white cables radiating gracefully from it, giving the structure a dynamic, sculptural presence on the Dallas skyline. Opened in March 2012, the bridge not only serves as a major transportation link, but also symbolizes unity between North and South Dallas. It has spurred revitalization and economic development in West Dallas, especially around the popular Trinity Groves area, known for its restaurants, music, and outdoor patios. Constructed as part of the Trinity River project, the bridge cost over $100 million and has won several engineering awards. With its elegant design and social impact, the Margaret Hunt Hill Bridge has become a beloved architectural landmark and catalyst for urban renewal in Dallas. The Margaret Hunt Hill Bridge is a striking cable-stayed bridge in Dallas, Texas, designed by Santiago Calatrava. Spanning the Trinity River, it connects Spur 366 to Singleton Boulevard and features a 400-foot-tall central arch supporting 58 white cables. Opened in 2012, the bridge is part of the Trinity River project and cost over $117 million. Its elegant design has earned several awards, including recognition from the American Society of Civil Engineers. The bridge is a landmark structure that enhances the Dallas skyline and exemplifies modern civil engineering and architecture. The Margaret Hunt Hill Bridge and the Margaret McDermott Bridge are two iconic structures spanning the Trinity River in Dallas, both part of the ambitious Trinity River project. The Margaret Hunt Hill Bridge, designed by world-renowned architect Santiago Calatrava, is a cable-stayed bridge known for its striking 400-foot steel arch and 58 twisting white cables. It stretches 1,206 feet and carries 6 lanes of vehicular traffic, connecting Spur 366 to Singleton Boulevard. Construction began in 2005 and was completed in 2012, costing over $180 million. It has received international engineering and design awards and has become a symbol of Dallas's modern skyline. The Margaret McDermott Bridge, named after philanthropist Margaret McDermott, replaced the aging I-30 bridge. While also featuring Calatrava's influence, this bridge is a conventional concrete freeway bridge, with added steel arches for pedestrian and bicycle paths. Construction began in 2012, but design flaws delayed the full opening until 2021. The freeway portion opened in 2013, while the arches faced setbacks due to wind-related structural failures. Repairs exceeded $7 million, and disputes arose between the city, engineers, and contractors. Despite its challenges, the bridge now serves both vehicles and non-motorized traffic, completing a vision of integrated urban mobility. Together, these bridges reflect Dallas's investment in innovative infrastructure and public space transformation. On April 16, 2011, construction workers began installing the first pair of suspension cables on the Margaret Hunt Hill Bridge's central arch over the Trinity River in Dallas, Texas. This marked a major milestone in the bridge's construction. The steel arch, manufactured in Italy, stands 400 feet tall. The cables were carefully lifted and attached to the arch, forming part of the structure's striking cable-stayed design by Santiago Calatrava. The all-out Trinity event brings vibrant energy to the Margaret Hunt Hill Bridge, with a unique run that celebrates community, wellness, and inspiration. As participants gather on this iconic Dallas bridge, the atmosphere is charged with positivity and determination. Set against the backdrop of downtown, the run is more than just a fitness challenge. It's a celebration of life, dreams, and the belief that anyone can be, quote, larger than life. Step by step, runners move forward to the rhythm of uplifting music and encouragement, embodying the spirit of hope and unity. The open bridge becomes a stage where people of all ages chase their goals and reach for the stars literally and metaphorically. Whether you're running, walking, or just soaking in the moment, the event reminds everyone that the future is bright and the possibilities are endless. All Out Trinity is not just a run, it's a powerful movement. The Margaret McDermott Bridge in Dallas, Texas, is a concrete pier and beam freeway bridge with striking cable-stayed bike and pedestrian arches. Partially designed by Santiago Calatrava, it replaced the aging I-30 bridge and forms part of the Trinity River and Horseshoe projects. Illuminated against the Dallas skyline, the Margaret McDermott Bridge transforms into a striking nighttime landmark. Two dramatic steel arches, each soaring to about 350 feet, frame gentle reflections across the Trinity River, creating a serene symmetry on still water. Pedestrian and bicycle paths hugs these glowing structures, offering peaceful transit beneath soft lighting. The nearby city lights further accentuate its graceful silhouette, making it a captivating urban vista after dark. Bridge assembly process by King Fabrication. At King Fabrication, the bridge assembly process is designed to be efficient, precise, and compliant with the highest industry standards. Once structural components are fabricated in the shop, the assembly phase begins on-site, where foundations and supports have already been prepared. The company's emphasis on prefabrication allows for a faster and safer installation process in the field. Prefabricated modules, such as girders, pipe arches, and truss sections, are transported to the job site. These large elements arrive in partially or fully assembled segments, ready for final installation. Heavy-duty cranes and rigging systems are used to lift and accurately position each section. During this process, the crew follows exact specifications from engineered shop drawings to ensure perfect alignment. The structural connections between components are either bolted or welded on-site. All welding operations adhere to AWS codes D1.1 and D1.5, ensuring strong and lasting joints. Bolted connections are made with high-strength fasteners and are torqued to meet design requirements. The entire assembly process is carried out under strict quality control procedures, including inspections and alignment checks. To maintain precision, laser-based surveying tools are used throughout the installation. Each part must fit perfectly within the larger structure to meet load-bearing requirements and safety codes. The assembled structure is continually reviewed to comply with AISC standard practices, AASHTO guidelines, USACE regulations, and state-specific DOT standards. In more complex bridge designs, temporary bracing or supports may be installed during the assembly phase to ensure structural stability. Once the main span is complete, crews move on to installing the bridge deck, expansion joints, and railings. By completing as much work as possible in the fabrication shop, King Fabrication minimizes time on site, reduces traffic disruption, and enhances safety for both workers and the public. Their methodical approach ensures that each bridge is assembled with precision and built to perform for decades. The assembly of the prefabricated Dallas Street Bridge begins with the delivery of massive pre-built bridge segments to the construction site. These segments, fabricated under controlled shop conditions to ensure precision and compliance with standards, arrive ready for immediate placement. Two large cranes are mobilized on-site to perform the critical lifting operations. Working in close coordination, the cranes carefully hoist each prefabricated bridge section from the transport trailers. Due to the size and weight of the components typical of heavy truss or girder bridges, the lifting process is executed with extreme precision. Each section is then slowly maneuvered into position over pre-prepared concrete supports. The workers on site assist with alignment. guiding the segments into place using tag lines and hand signals to ensure millimeter accuracy. The segments are then lowered gradually, with continuous communication between crane operators and ground crews to guarantee safety and structural integrity. Once the segment is seated properly, the crew begins securing it with bolts and temporary supports. This process is repeated for each segment, forming a seamless bridge structure as they are connected end to end. Throughout the operation, all actions are performed according to AASHTO and project-specific requirements, ensuring stability and long-term durability. The prefabricated arch bridge at US 52 and the Salem Creek connector was assembled using a highly coordinated sequence of heavy lifting and placement. The construction process began with transporting the large prefabricated bridge sections to the site. Each piece had been precisely fabricated off-site under controlled shop conditions to ensure quality and minimize fieldwork. On-site, massive cranes were employed to carefully lift the arched steel bridge sections. These cranes positioned the components with precision onto the pre-prepared supports. Workers guided the placement to ensure perfect alignment and fit between the segments. Once the arch segments were in place, crews secured the structural connections to create a unified bridge span. Final adjustments and bolting ensured the bridge met all alignment and safety specifications. This efficient assembly minimized disruption to traffic and surrounding infrastructure. By prefabricating the structural components, King Fabrication streamlined the on-site construction phase. This approach allowed for faster installation and reduced construction complexity while adhering to standards. The result was a successful and timely installation of the iconic Winston Salem Arch Bridge. The construction of the third Bosphorus Bridge's pylons began with the assembly of slipform equipment at the base. Once assembled, the slipforming process commenced, enabling continuous and fast vertical construction. The slipform climbed to the structure as concrete was poured and reinforcement installed simultaneously. Crews worked around the clock in shifts to maintain momentum. The pylons, triangular in cross-section with 1.50 meter thick walls, were steadily built up to a height of 208 meters using this method. The concrete mix was specially developed to ensure high durability and performance. As the slipform rose, platforms and support systems were adjusted to maintain stability. After reaching the designated height, construction continued using conventional climbing formwork. The process achieved remarkable efficiency and precision, forming the A-shaped pylons of what would become the tallest suspension bridge pylons in the world. Workers built a series of viaducts to span deep gullies in the Sugarloaf mountain range using balanced cantilever construction. Precast concrete segments and columns were produced in an on-site precast yard to improve speed and quality. Segments were placed symmetrically from each pier and post-tensioned with steel cables. A 165-meter-long launching gantry lifted and transported segments into position. Strict environmental controls minimized vegetation clearing. 3 major viaducts up to 350 meters long and 39 meters high were constructed, overcoming logistical and terrain challenges with innovative, efficient techniques. Crews completed segments F1, F2, and G of the SH99 Grand Parkway by building over 38 miles of divided highway, clearing 2,100 acres, and relocating 400 utilities. More than 120 bridges, including 4 interchanges, were constructed. Despite record flooding, Zachary met the accelerated schedule by creating an on-site precast yard, producing 432,000 feet of bridge beams and pouring 660,000 cubic yards of paving concrete. Nearly 4,000 beams and 45,000 deck panels were installed, completing the largest TXDOT design-build project in just over 2 years.